Are you ready to start now?
Yes, sure.
Great. Yeah, so welcome everyone, and today we're very happy to have Salvatore Floccari from the University of Bielefeld, and he's going to tell us about K3 surfaces associated with varieties of generalized Kummer type. So please go ahead.
Yeah, thanks a lot. I'm happy to give this talk. So thanks to Flora for the invitation, and thank you for having me. I will discuss this work where I studied some K3 surfaces which are naturally associated via Hodge theory to a family of hyperkähler varieties, namely these of generalized Kummer type. And then I will discuss some consequences of this for the Hodge conjecture, that there has been in the past years quite some progress, mostly due to Markman. I will explain it later. So let me start by just, if it works, by just recalling what the Hodge conjecture predicts. So we work over the complex number, and for any smooth and projective variety, one considers the singular cohomology groups. Now these are finite dimensional vector spaces, but they carry pure Hodge structures. So HK will be a pure Hodge structure of weight K. And remember, this means that when I tensor it with C, I get a decomposition into P plus Q pieces. Oh, sorry, sum over P plus Q equal K, so pure weight K of H P plus Q X, such that complex conjugation induced on this complex vector space exchanges P and Q, basically. And then one looks at the space of Hodge classes, which by definition are those classes in the 2K cohomology, rational cohomology of X, which belongs to the KK part of the Hodge decomposition. So you see that complex conjugation will exchange this, will send this HKK to itself. So this is a real subspace, and then we take the rational points, and these are the Hodge classes. And somehow, why they come up naturally is because of the following effect, that if Z is a subvariety of codimension K, then the corresponding cohomology class given by integration of differential forms on Z, so it has codimension K, so we get the cohomology class in the 2K cohomology. And this class is in fact a Hodge class. And now the Hodge conjecture asks whether the predicts that the converse is true. So conjecture every Hodge class on any smooth projective variety X is so-called algebraic, by which we means that it is a linear combination with Q coefficients of fundamental classes of subvarieties of X. So this is the Hodge conjecture, well-known, very difficult problem. So perhaps the best evidence we have, the most the best general result is that by Lefschetz theorem on 1-1 classes, the Hodge conjecture holds in codimension 1. So in H2 of any smooth projective variety, we know that every Hodge class is algebraic, in fact, represents a divisor. So I write in codimension 1, this means in H2. Okay. Oh, what's going on? Okay, sorry. Okay, sorry, I don't know how to erase this. Anyway, this is the best evidence, but of course, this was before the Hodge conjecture. Lefschetz proved this theorem in 1924. So, of course, Hodge was motivated for his conjecture by the theorem of Lefschetz, which says that algebraic classes in codimension, Hodge classes in H2 have a geometric interpretation, and essentially Hodge was asking whether one can do something similar in higher codimension. Then, okay, the Hodge conjecture is known for some varieties of which we understand the geometry very well. For instance, projective spaces or Grassmannians, maybe, yeah, also flag varieties. But okay, in these cases, the whole cohomology is generated by algebraic classes, and we can really understand very well the situation. And also the Hodge structure is therefore very simple. It just consists of Hodge classes, the cohomology. So a very interesting case that will be also related to my talk is that of abelian varieties. This has been studied by various authors, and probably it was started by Mumford and Tate. Then also Moon and Zarin more recently in the end of the 90s. We know now that the Hodge conjecture holds for any abelian variety, which is isogenous to a power ak with a of dimension at most 3. So yeah, I should have said here that the Lefschetz theorem implies that Hodge conjecture holds for varieties of dimension at most 3. For varieties, all curves, surfaces, and trifles. But here, so we know it for A with this dimension, but then one subtlety in proving the Hodge conjecture is that if you know it for a variety, then there is no way to get it for the powers of these varieties. So this result is non-trivial, does not follow from Lefschetz theorem in an obvious way, but ultimately it follows from the Lefschetz theorem. In fact, the reason why the Hodge conjecture holds for an abelian variety as a genus to a power of a low-dimensional abelian variety is that all Hodge classes in the cohomology of this AK under this assumption are obtained as a cup product of divisors classes. So any Hodge class in this cohomology group can be obtained as intersection of Hodge classes in H2, but these are algebraic by Lefschetz theorem. So when we intersect them, we still get classes which are algebraic. And so one reduces the Hodge conjecture for these abelian varieties to the Lefschetz theorem on 1-1 classes. And so here the proof is that one has to show this property that the Hodge classes, the subalgebra of Hodge classes is generated in degree 2, essentially. So it involves representation theory techniques. And in fact, if one reading the Grothendieck-Serre correspondence at some point, Serre is in the US and informed Grothendieck that Mumford and Tate have undertaken this program of showing that on an arbitrary abelian variety, every Hodge class is intersection of divisor classes. That's what they believed at first, it seems. But then Mumford and later also Weil found example where this fails. So there exist, starting from dimension 4, there are abelian varieties containing so-called exceptional Hodge classes. So exceptional, I mean that cannot be expressed as intersections of divisors. And so for this such an abelian variety, these Hodge classes, of course, it's a difficult case of the Hodge conjecture. And let me maybe recall what are these, how one gets such things. So these are the Weil type abelian varieties. So a 2n dimensional abelian variety is called of Weil type if there exists a quadratic imaginary field q square root of minus d, where d is a positive integer, contained in the rational endomorphism algebra of A. And moreover, one requires some sort of symmetry condition. So we have this field acting on our abelian variety, and one required some symmetry. So the action on the tangent space at the origin as n-dimensional eigenspaces for both eigenvalues I square root of d and minus I square root of d. So one requires this symmetry. And then the point is that now we can view H1 of A Q. Actually, this becomes, since we have this action, is n-dimensional. So this is a 2n, this is a 4n dimensional over Q, becomes a 2n dimensional over square root of minus d. And yeah. And then one takes this exterior power as a k-vector space. And one shows that this embeds into the middle cohomology. So if we take the exterior power now over Q, sorry, I should write H1 AQ. Now if take this embeds here, and this is just the middle cohomology of our A. And one showed that this is now a two-dimensional rational space. And the image consists of exceptional Hodge classes. So to show that they are Hodge classes, one uses these properties on the eigenspaces. But in any case, yeah, these are the hard case for the Hodge conjecture for these varieties, and these are called also Hodge-Weil classes. And in each dimension, in each even dimension, 2n, we have that these veil type 4 folds, veil type 2n folds come in countably many families, which are parameterized by this quadratic field, so the integer d, by the field q square root of minus d. And then one can associate to any fourfold another discrete invariant, which is called discriminant. I will not really define it, but basically one takes any such veil type abelian variety, and then one can construct a special polarization, which is in some sense compatible with the field action. And then basically this discriminant is an invariant of this polarization. So these are these abelian varieties of veil type, and by the work of Munen and Zarin I mentioned earlier, in the 1999, they reduced the Hodge conjecture for abelian varieties of dimension 4. So already here, the Hodge conjecture remained open until actually a couple of months ago of dimension 4. So Munen and Zarin proved that the Hodge conjecture is true for any such four-dimensional abelian varieties, which is not of veil type. And actually, in January, finally, Markman. Okay, some more cases were proven by Schoen in the middle for some of these veil fourfolds. But by this work of Munen and Zarin, one needs to prove the Hodge conjecture for all fourfolds of veil type. And this was proven by Markman in January this year, that the Hodge conjecture holds for any fourfold of veil type. So that's quite an amazing progress, because with this result, he completes the proof of the Hodge conjecture for all abelian fourfolds. But I want to mention a previous result by Markman that he obtained a few years ago. And so, yeah, this is the most recent result he has, but before he had already proven the Hodge conjecture for some of these fourfolds. So he proved that for any veil fourfold of discriminant 1, the Hodge veil classes are algebraic. For any fourfold of veil type with discriminant 1. So, of course, the result he proved later, so this is like in 25, and this, I think it was in 2019. So, of course, the most recent result is much more stronger, and but the older result is obtained using a relation, a connection between such a fourfold, so veil type with discriminant 1, and hyperkähler varieties, so-called of generalized Kummer type. So this will be more relevant for my talk, and essentially I will now define this hyperkähler of generalized Kummer type and explain what's the relation with these fourfolds. And then my contribution will be to put consider also some K3 surfaces into the picture, which allows us, which are both related to these hyperkähler varieties and therefore to these fourfolds of wild type with discriminant 1. So yeah, this what I wanted to recall about the Hodge conjecture. Of course, feel free to interrupt me and ask questions. Now, before going further, I should maybe introduce and recall some things on hyperkähler manifolds. So, by definition, X is a hyperkähler manifold, is a compact Kähler manifold, such that a hyperkähler manifold X is, a compact Kähler manifold such that pi1 of X is trivial, so X is simply connected, and the space of holomorphic two forms on X is one-dimensional, generated by the class sigma of a symplectic form. So symplectic means that if I have a section of this omega 2, so I can look at each point. This section will induce me a pairing on the tangent, alternating pairing on the tangent space at each point. And the symplectic means that this pairing should be non-degenerate at any point of X. So it's quite a strong condition. And for instance, in dimension 2, okay, the existence of this non-degenerate alternating pairing on the tangent space already tell me that the dimension must be even, because it has to admit this non-degenerate alternating pairing. And if the dimension is 2, actually X is a K3 surface, because we get, so if the dimension is 2, then the non-degeneracy of the form, basically, you know, omega 2 is just the canonical sheaf, so it just says that the canonical sheaf is trivial. So we get simply connected Kähler surfaces with the trivial canonical bundle. And indeed, the canonical bundle of any hyperkähler variety is trivial, because you can just take the suitable power of this section will trivialize the canonical bundle. And in some sense, the general theory of these higher dimensional manifolds, it's actually very close to the theory of K3 surfaces. So perhaps just want to give you a couple of points that the main object to study a hyperkähler variety X, the main object to look at is the second cohomology group. So you see, while this is natural for a surface, so for a surface, these cohomology groups, of course, contain all informations, but for an higher dimensional variety in general, these may contain very little information. But somehow for hyperkähler, this is the philosophy, at least, is that this should contain almost all essential information. And by definition, this is equipped with a Hodge structure of K3 type. So this means that the Hodge numbers H20 and H02 are 1. But so this is just because the H20 part is exactly isomorphic to this vector space. But also, a remarkable fact is that there exists a symmetric bilinear form Qx on H2 integral on H2xz called the Boville-Bogomolov form, which is, so basically this is an analog of the intersection product that we have on a K3 surface. So this is non-degenerate, on the generate of the signature 3 positive, and then okay, denote by B2 the dimension of this H2. So it's 3 and B2 minus 3. Moreover, it's compatible with Hodge structures. But this form is topological. I mean that it doesn't depend on the complex structure of X. It's just some form that we get from the structure of the cohomology of the variety. But so essentially the consequence is that when we deform X, then in a family of hyperkähler, smooth holomorphic family of hyperkähler manifolds, then the H2 of the fibers with the corresponding form, it actually is always the same lattice. So it doesn't change under deformation. And one thing I find useful to understand this form is the so-called Fujiki relation, which says that for any class in H2, this form can be understood. So it says that there exists a constant, rational constant Cx, which again doesn't only depends on the topology of X. So if I change the complex structure, this doesn't change, such that for every class in H2, I look at the top, so the top intersection number of gamma to the power dimension of X. This will be in the top cohomology group of X. It will just give me a number. And this is this constant times the value of this quadratic form on H2 on the vector gamma. And we take the power dimension of X over 2. This makes sense because dimension of X is even. So you see that on an arbitrary variety, we can always look at this form sending top intersection form of divisors. But of course, here there is the non-trivial statement that this form admits nth root, basically. So that's how this form can be understood. Okay. And so what I mean that this is the main player in the theory of hyperkähler manifolds is that, for instance, one formulate a Torelli theorem, Torelli type theorems in terms of Hodge structures on the lattice H2 xz with this form qx. So perhaps to briefly recall how it works, one consider, so if X is any hyperkähler, then let me set lambda for the isomorphism type of this lattice. Then one look at the so-called moduli space of lambda marked hyperkählers. So here Y is an hyperkähler and eta is an isometry from the Bouville-Bogomolov lattice of Y to this lambda. So we are looking at all hyperkählers with this fixed second cohomology as a lattice, modulo natural notion of isomorphism. And then on the other side, so this is basically a moduli space of the objects we want to parameterize up to these markings that we have to introduce. And then on the other side, one takes the so-called period domain, which consists of all lines in the projectivization. So all the lines in lambda tensor C, where they satisfy, so the form will be isotropic on this X, but when I look at X paired with the complex conjugate, it will be positive. So this space here is the period domain, so it parameterizes Hodge structures of K3 type on the lattice lambda. So, I mean, if you take a point X here, X, which Hodge structure gives me, then you set the choose zero part of lambda to be the line spanned by X. So, I mean, X is a line in lambda tensor C. So here I have to give a decomposition of lambda tensor C. And then you take as a 0,2 part X bar. And as 1,1 part, you just take the orthogonal to the plane X bar. So that's how you get the Hodge structure of K3 type. You see that the choose zero part is one-dimensional from this period domain. And then one uses deformation theory to see that this is a non-Hausdorff. Okay, there is this issue, but in any case, it is a smooth. So every point has a neighborhood, which is a neighborhood of the origin in Cn. So it's a non-Hausdorff complex manifold of dimension, the rank of lambda minus 2. And then one looks at the so-called period map P, which is defined by sending y eta. Oops. Sends a marked hyperkähler y eta to the line eta. So I can use my isometry eta to send H20 y to a line in lambda tensor C. And one then checks that actually this will satisfy these equations, so it will land into the period domain. And then the Torelli theorem says that the map P is, I mean, one, I'll give just not the strongest version, but the local Torelli theorem says that P is a local isomorphism. And moreover, the period map is surjective. So for any component, so the space of moduli of marked hyperkählers may have many connected components, but for any component, the restriction of the period map is surjective onto omega lambda. And in fact, one can also show that P for any component is generically injective. Yeah, here perhaps I should mention, yeah, Boville, Huybrechts, Verbitsky. Prove this statement. In any case, what I like to emphasize is that this map is surjective. So if the upshot is that if X is any hyperkähler, it will deform in a family of hyperkählers of dimension B2 minus 2. So whenever we find one example of a hyperkähler, actually they come in big families. And if we want to look at projective deformations in these families, actually they form countably many families. Of dimension now B2 minus 3. So, okay. And let me now briefly recall the known families. So one wants to classify hyperkählers by deformation. And this classification is an open problem. So by now we have some examples, but yes, it's unknown whether these are all or not. And so the first examples are, of course, K3 surfaces. The first family, the only family in dimension 2. Then for every 2n, even dimension, we have 2 families in this dimension that we know for any n, namely the K3n type. So these are by definition the formations of Sn, where S is K3, and this guy here is the Hilbert scheme, so-called the Hilbert scheme of points on S. So more precisely, it is the Hilbert scheme parameterizing zero-dimensional subschemes of length n. So if I have a zero-dimensional subscheme, yes, I mean that the generic element here, length n, zero-dimensional subscheme, generically, such thing is unordered set of n points on S. So in fact, this Sn is a resolution of the n symmetric power of S. That's the Hilbert-Chow resolution. And then one starts with the K3, and one can show that this Hilbert scheme is in fact a hyperkähler manifold. And we have this example in every dimension 2n. Then there is another family, which is the generalized Kummer type from my title. These are the Kum n type hyperkählers. And what they are deformations of the so-called generalized Kummer variety, KNA. Is the generalized Kummer variety on abelian surface A. And how is this constructed? Again, you start from A, you build up this Hilbert scheme now of n+1 points. Now this has this Hilbert-Chow morphism to the symmetric power of A. But now we can take further another map by sending n+1 points on A. We just send them to their sum using the group law that we have here in A. So let me call phi this composition. Then it is known that phi is isotrivial. So all fibers are isomorphic. And we take the fiber over 0 as our KNA. And then the Beauville has shown that this is a hyperkähler for any n of dimension 2n. And in fact, also the Betti numbers are known. Just to give you some information, here the Betti number is 23. And here the Betti number is 7. Then there are 2 examples, 2 families found by O'Grady, commonly called OG10, OG6, and 10 and 6 is the dimension in which they live. So for any even dimension, at least 4, we have these 2 families. And then in dimension 6 and dimension 10, we have 2 more families that were found later by O'Grady. So yeah, that's the situation. And now I will focus on these generalized Kummer type varieties. So here, the main observation behind this work I'm telling you about is that the second Betti number, first, I want to remark the following thing, that a abelian surface, so it deforms in the family of complex tori of dimension 2. So it deforms in a 4-dimensional family of holomorphic manifolds. If we just look at the abelian surface or projective ones, we get 3-dimensional families. But yeah, from tori, we get a 4-dimensional family, and the construction of the Beauville-Kummer variety works also if A is not projective. So this gives me a 4-dimensional family of complex manifolds of Cum n type by taking the family K n A. Now, however, by the Torelli theorem that we just recalled, there exists a 5-dimensional family of Cum n manifolds. So from this, we see that the very general variety of Cum n type, and similarly, right, if we take polarized families of abelian surfaces, I mean families of abelian surfaces, we get only 3-dimensional families, but families of projective varieties of Cum n type, they form dimensions of dimension 4. They form families of dimension 4. So the very general variety of Cum n type is not of the form Kna. And in fact, there are generalizations of the construction of this Kna by taking moduli spaces of stable sheaves on A. But also with this generalization, one cannot get all Kummer type varieties, Kummen type varieties. In fact, the very general will never be accessible in this way. And in fact, it is quite hard to describe such very general variety of Kummer n type. So one problem I'm interested in is that there is no known description, for instance, of a variety of Cum n type of a projective variety of Cum n type of Picard rank 1. In fact, the methods we have to construct these from abelian surfaces only always give us varieties of Picard rank at least 2. And for the other infinite series, like for K3 n type, there are some constructions of very general varieties of K3 n type with Picard rank 1 in some, I mean, there are some constructions. Also there, the general picture is maybe not complete, but for instance, starting from cubic fourfolds, one can construct complete families of K32 type and also for other values of n. However, for varieties of generalized Kummer type, for the time being, there is no explicit construction. We only know they exist by the Torelli theorem, but describe them geometrically is a different story. And yeah, so yeah, this is some problem. And I would say that in recent years, it has been understood that one should look for such a construction not starting from an abelian surface, but starting instead from a K3 surface.
By curiosity, could I ask a question? So do we know that some so modularized space of polarized general type Kummer is unirational for some abstract reason?
Yeah, this I'm not so sure. I know there are some. I think maybe they gave some example, but I think that the situation also there is less understood than for K3n. But yeah, I think in general we expect for low degree of depolarization it should be unirational and. But yeah, actually, I think I think it's not known. I think actually there are some example proving that is it's not unirational for large degree.
Yeah, but for small degree, so even regarded as abstract moduli space or like quotient by symmetric bounded domain, there is no some unirational parametrization, maybe not
Yeah,
modular.
yeah,
This
exactly. I think it's not known, right? Yeah.
Thank you.
Yeah. And so we instead of instead of trying to construct from an abelian surface, which seems impossible, one should look starting for such a construction starting from some maybe K3 surface. So somehow one would like to have something like A. So here we have our generalized Kummer variety, and then I mean in this case we have quite a knowledge of this generalized Kummer variety through the fact that it is built out of A. When we deform it, we lose A, but somehow the idea is that one can instead consider K3 surfaces and get something which reminds, because in this case, if you start from K and A, one, yes, has built it from A, but there is a natural K3 surface associated to this. One can look at the Kummer K3 surface associated to A. By definition, this is the minimal resolution of the quotient of A by -1, these are 16 nodes. And then there is such a K3 surface. And so we are trying to generalize this relation. Now, by the level of Hodge theory, this can be done rather easily. So what we know here is that if we look at the transcendental part of the cohomology of K and A, so here the transcendental part is the orthogonal to the Néron-Severi group, or if you want, the smallest sub-Hodge structure containing the H20 part. Here we have a known description. This is a Hodge isometric, so both as a lattice and a Hodge structure. This is the same as the transcendental cohomology of A. And on the other hand, it is known that transcendental cohomology of the Kummer K3 surface is Hodge isometric to the transcendental cohomology of A with the form multiplied by 2. Okay, so this is at the level of Hodge theory and the lattices, the relation that we have in this case between this K and A and some natural K3 surface associated to it. So now, very simple idea is to just mimic this definition. So let K be any variety of cum n type. So here, when I say variety, I usually mean projective of cum n type. And now, okay, let Sk be the K3 surface such that there exists a Hodge isometry between the transcendental lattice of the K3 surface and the transcendental lattice of K with the form multiplied by 2. Okay, so now I should justify that this definition makes sense. So Sk exists and it is unique up to isomorphism. This essentially follows just from the Torelli theorem of K3 surfaces because the Betti number of K is small. So since the second Betti number of K is 7, and we are looking at K projective, so there exists at least an ample class, this, it's K, this transcendental lattice has a rank at most 6, and the signature is 2. So when I take the transcendental part, I need to remove a positive class in the Néron-Severi because I'm on a projective variety. And so the signature will be 2 positive and K, K maybe is not the best letter, say M negative. But any such lattice can be embedded in the K3 lattice. So K3 lattice, I mean just the lattice, which is the second cohomology of a K3 surface. Now by the Torelli, so we get this sublattice with a Hodge structure, and it has the right signature. And this means that by the Torelli theorem of for K3 surfaces, yes, so the same works when I multiply the form by 2, doesn't matter. So by the Torelli theorem for K3 surfaces, there exists K3 Sk, whose transcendental lattice is Hodge isometric to this. To this H2 transcendental KZ2. In fact, you can see that from this that the 2 is not important for the existence of this K3. I just so it's a choice that I just make it because in this way, when I start from the generalized Kummer variety, I get the Kummer surface on the abelian surface. So that's why this seemed to me the most natural choice. But in any case, by the Torelli theorem, this exists. In fact, Torelli theorem, one can see it as saying that for any Hodge structure of K3 type on this lattice, there is a K3 with that Hodge structure. So that's what we're doing here. And moreover, Sk is defined up to isomorphism because Sk has Picard rank. So the Picard rank of Sk will be 22 minus the rank of the transcendental cohomology of K. But this is at most 6. So in any case, this is at least 16. And so it is uniquely, so it is determined up to isomorphism by the lattice, transcendental lattice with its Hodge structure. So that's a general theorem that K3 surfaces of Picard rank at least 12, projective K3 surfaces of Picard rank at least 12, they are determined up to isomorphism by the transcendental lattice. The point is that since this transcendental lattice is small, so if we have 2 K3 surfaces with Hodge isometric transcendental lattices of small rank, then the Hodge isometry between the transcendental lattices can be extended to a Hodge isometry between the whole second cohomology. And so by the Torelli theorem, the K3 are isomorphic. So that's the explanation on why we find this K3. So with this definition, yes?
Does the embedding of the lattice inside the K3 lattice matter in the proof of uniqueness? Like if we choose a different embedding, then
Yeah, the point is that since this is a small lattice, the embedding is unique up to isometry.
okay.
That's actually the point that allows you to extend the isometry you have on an isometry you have between these transcendental parts to a global isometry of the H2.
Okay, thanks.
And it's just because the rank is small. So by standard results on lattices, you get that the embedding is unique up to isometry, and you can conclude.
Okay, yeah, thank you.
Yeah, no problem. Okay, so now we have this K3 surface just associated by Hodge theory to our any n variety K. So now, according to the Hodge conjecture, if you want, this fact predicts some that there should be some geometric relation as well between these two. In fact, the isometry defining SK, Hodge isometry. So now for any K, this will correspond to corresponds to a Hodge class in H2 SKZ dual tensor H2 KZ. And okay, the dual I can identify with H2 since I'm on a surface. So I can view this as a sub space of H4 by the Cournot formula of H4 SK times K, comma Z. So by the Hodge conjecture, we expect that there exists an algebraic cycle on SK times K, inducing the Hodge isometry, let me call it phi, inducing the Hodge isometry phi. So this Hodge class is algebraic. It means that there must be some subvariety in SK times K, or rather a linear combination of classes of subvarieties, such that when I look at the action as a correspondence, it induces this morphism phi. And so that's what I can prove, that there exists a way to relate geometrically K and SK. So I will prove this, and it will be a consequence of the following statement. So for any projective K of cum n type, there exists a subvariety W, K, which is a hyperkähler of K3 M type, where here we have either 2m equal n, so if n even, or 2m minus 1 equal n. Yeah, n type here, n, it's always at least 2. So for n odd. So you see that the dimension will be roughly half. I mean, it will be exactly half in this case and a bit more in this case, such that WK is a moduli space of stable sheaves on the K3 surface SK. So let me say what this is. This is a moduli of stable sheaves with Mukai vector V. So basically, this taking the moduli of stable sheaves on K3 surfaces is a generalization of the procedure of the Hilbert scheme to get hyperkähler varieties of K3n type. And again, in general, a K3n type variety is not a moduli space on any K3 surface. But here, you see that we are taking some I will explain it later, but in this case, this WK is a special K3n variety, which can be constructed as a moduli space of stable sheaves on a K3 surface, on the K3 surface SK. So here we are taking sheaves. The Mukai vector is basically, we are fixing its cohomological invariant, basically the Chern classes. And then there is a stability condition that one needs to take to account. But okay, let's not go much in details into that. The point is that as a corollary, we get that the isometry, so the Hodge isometry H2 SK Z to H2 transcendental KZ 2 is algebraic, so it's induced by an algebraic cycle. And here you will see I actually, to be precise, I think to be safe I should tensor with Q, because what I get, I forgot here a statement, part of the statement. Okay, let me remove this. So one important consequence of the statement is that if I denote, important part of the statement is that if I denote this by I, the inclusion, then such that the inclusion, the pullback along the inclusion H2 M H2W K is injective and multiplies the form by factor 2. So it's not an isometry, but multiplies the form by factor 2. And in fact, it induces a primitive embedding of lattices and also compatible with the Hodge structure. So once I rescale the form on the left-hand side by 2, this becomes a primitive embedding of lattices and Hodge structures. Okay, so sorry, I forgot this, because now how you get that this isometry is algebraic? Well, first of all, we have that the pullback is clearly given by an algebraic cycle, namely the graph of the inclusion. So you get, we get an algebraic cycle giving a map in this way. And so, in particular, this will be a Hodge isometry between the transcendental lattices. So I can restrict it. And this is an algebraic map. So I mean, given by an algebraic cycle. And on the other hand, by general theory, so on moduli of sheaves on a K3 surface, it is known that on SK, I mean, this is for any K3 surface and any smooth and projective moduli of stable sheaves on it. So I take over here, I have what is called a semi-universal sheaf. Say U, And then I can take a class C. I can take a class which is given by the Chern character of U times the Todd class of S times the moduli space. Now here I take the Kunet component in degree 2. Yes. And then okay, this is algebraic because I know the standard conjectures for this space here. Let's not worry too much about it, but this operation of taking the Kunet component is only conjectural in general algebraic, but in this case, this is an algebraic cycle and every Kunet component remains algebraic. And then I look at this as a correspondence. This will induce me an isometry. It is known, this by work of Mukai, O'Grady, that this class here, okay, up to a multiple actually should take, there is a factor one should take here, but doesn't matter. In any case, this induces an isometry between transcendental lattices. And this is also induced by an algebraic cycle. So now so now I want to put together these two, but okay, I need to invert one of them too. And you need to show that the inverse is given also by an algebraic cycle. But yeah, I mean, the way I do it, I just apply some general known results on motives. So I know that when I go to Q coefficients, this inverse will also be given by an algebraic cycle. But a priori with Z coefficients, I'm not so sure. So to be safe, I get, I just state it with Q coefficient, and I get a cycle giving the inverse. So from H2 WKQ, the transcendental cohomology of SKQ. And now I can just compose. So let me call this psi. And then I can get I star composed psi will give me, okay, actually I wrote it in the other direction, but this is an algebraic correspondence inducing the isometry, Hodge isometry I want on transcendental lattices. Okay, so this moduli space here gives me the geometric relation I seek between K and the K3 surface SK. And now let me maybe sketch the proof of the theorem that I can always find this moduli space. The idea is the following. So there is a general result which I'm going to use. Let X be a hyperkähler, any hyperkähler, and then look at the group out 0 of X. This is the group of automorphism such that the induced action on the second cohomology is the identity. And then there is a theorem by Asset and Schinkel, which tells me that this group is a deformation invariant. So this means that if I have a holomorphic family of hyperkählers, then these groups will arrange into a local system of groups fiber-wise. And so a consequence is that if I take X over B, X over B, a family of hyperkähler family, Then I look at, I fix one fiber, and I look at some element in this group. Now, yeah, there is another general result by Huybrechts that says this group is always a finite group. But in any case, now I look at a component Z, which is a component of the fixed locus of G acting on this fiber. Then using that this fact is that this group is deformation invariant, I can find a finite étale base change. So basically, étale base change B to, so I can take a B to B prime to B, and base change there. I mean, I will ignore it for the notation, but somehow the point is that the monodromy may not act trivially on Z, but it will move it into other finitely many components. So up to a finite étale base change, I can trivialize the monodromy action of Z, and I get a smooth family, which is now a subfamily Z over B prime, and now this will be contained in X. So essentially, this argument shows that for any component of the fixed locus of this automorphism, then basically they deform together with X in all directions. And now, if K is of cum n type, I mean, this group out 0 is trivial for varieties of K3 n type, but for cum n type, this is not the case, and the automorphism group of K, trivial on H2, is isomorphic to Z mod n plus 1 to the fourth, semi-directed Z mod 2, where the second factor acts as the inverse map on the first. And this is shown by Boissier, Nieper, Wiskirchen, and Sarti. In fact, they compute that if you take the actual generalized, right, by the above theorem, we can compute this group for one specific example in our family. And in this case, one can look at the translations by points in A. So remember, you have this A n plus 1, then A n plus 1, and then A. And of course, translations by points of A, as well as -1, any automorphism of A acts on the Hilbert scheme by pulling back the subschemes. But now we gotta see which ones will preserve the fiber, which, so here I denote by an plus 1, 0, the fiber over 0. And one needs to see which translations will preserve this K and A. And it's not hard to see. I mean, it's easy to see that this automorphism trivial on H2 contains, I mean, yeah, it's not hard to see that this group here acts on the on the generalized Kummer variety. Then one uses a known description of the H2 of the generalized Kummer variety to see that this group is actually contained in the group of automorphism trivial on H2. And then these authors, they prove that actually equality holds, so that any automorphism of the generalized Kummer variety trivial on H2 is a composition of translation of a point of order n plus 1, torsion point, and the involution given by the inverse map. So what I do now to find this moduli space that I want, I check, I look at the fixed locus, look at K and A fixed locus by -1. Now the lemma is that this locus exists a unique component W fixed by this -1 of maximal dimension M, where we have either 2n equal 2m equals n if n is even, or 2m minus 1 equal n if n is odd. And moreover, this W is hyperkähler, and in fact it is isomorphic to the to the nth Hilbert scheme on the Kummer K3 surface associated to A. So it is hyperkähler of K3 M type. But then this means that by the previous remark here, that we can deform components of the fixed locus will deform in a smooth family for any deformation of K. We get that, yes, here we get that K any cum n type contains a K3M type hyperkähler, which is a deformation of this W. So here, what is this W? Well, if you look at the action, essentially you have to look at the action of -1 here, but okay, modulo studying this action on the fibers of this Hilbert-Choudhury solution, you can look at the action here. And here everything is very concrete and simple, and you see that an n+1 collection of points to be fixed, well, it has to have this following shape. You know, you can take so this W will be the sets of all the pairs of points. So if there is A1, then you should have also -A1, at least for the general point. It has to be like that. Then A2, you gotta have -A2. Then you write to AM and then -AM. And now if n, so you need n+1 elements. So if n+1 is even, then you take just this, or you take the points, you add at 0. Yeah, so not sure if this is how much this is clear, but if you think a bit about it, I want to make the point that everything is very concrete, because in this case we have this description of the action, which is quite concrete. Then by this abstract deformation result, we get that any cum n type contains such K3M type hyperkähler. And now the next step is to study the pullback along this inclusion. And here, it is not hard to see that this map is injective, because again, we can work in families, and the form, in fact, we can work in family, and it will be sufficient to prove this for the very general K. So sufficient to show it for very general K, in which case the H2, the odd structure is irreducible. So it's a Picard rank 0 complex manifold. Is irreducible odd structure. And now you just need to show, I mean, since it is irreducible odd structure, then this morphism, it's a morphism of odd structure. It's either 0 or it is injective. But using that again, so if you look at the point, so you just need to show that this is not 0. And to do this, you show that the restriction of the symplectic form is symplectic. And the argument is not hard, because at a point x of W, you have that the tangent space of at x of w at x is contained in the tangent space of k at x, and it's actually the invariant part of this under this -1. But this -1 is symplectic, so it acts here by isometries with respect to the symplectic form. It preserves the pairing, and you see it splits this tangent space, since this -1 is an involution, into the identity eigenspace and the minus identity eigenspace, and they are orthogonal for the pairing because they are eigenspaces of different eigenvalues. So if it was degenerate here, the form, it would be degenerate here.
So when you say very general, you mean like non-algebraic K?
Yes, yes. I mean Picard rank 0.
0.
So just a complex manifold. But this automorphism deform also to those. So it's fine.
So in particular, this WK are also trianalytic subvarieties.
Yeah, exactly. This WK is trianalytic. Yes. And in fact, for K varying in a holomorphic family maximal of Qman, we get the 5-dimensional family of these K3M type hyperkillers.
Okay, thank you.
Thanks. And yes, so yeah, this I wanted to say that since this is again, so the restriction of this is symplectic, so in particular it is not 0. This is how you show the injectivity. And then the other thing I think it's interesting to say is why I star multiplies the form by 2. I mean, this is a computation, but somehow I want to recall the following fact, that if you have hyperkähler, you take a cohomology class, maybe I should put 4, is called canonical Hodge class. If it remains Hodge on any deformation of X. So for hyperkählers of higher dimension, there are some of these canonical Hodge classes. Of course, one example is the Chern classes, but actually in the Kummer type, Kummer-N type, there are many more in general. And in fact, also this WK or W in the cohomology of K is a canonical Hodge class, because in fact, as we said, this W is trianalytic, so it deforms everywhere, so it remains algebraic, the class, in particular Hodge. And now the point is that Fujiki relation generalizes to say that alpha in H4K XQ canonical Hodge class, then exists constant C alpha, such that for any gamma in H2, you have that, so you can look at the pairing alpha, and then you take gamma to the 2n minus 2k, where dim of x is 2n. This now is a top class, so it's a number, and this is again proportional to a power of this Boville-Bogomolov Fujiki form on gamma. And now, if alpha is the fundamental class of W, then you see basically what I'm doing is that this thing here is the integral over W now of I star gamma to the 2m. I mean, the dimension will then match up. So essentially, this Fujiki relation tells me that, yeah, this will be m as well, But by this, I can just compute. By this, it will be sufficient to compute I star of beta for a single class beta in H2. Because then if I have this class beta, then I can get the Boville-Bogomolov square on the Kummer type variety. I get the Boville-Bogomolov value on the subvariety of K3M type. So I get this constant here, and then the same factor must arise for any gamma. So yeah, I just wanted to, and this is proven by some geometric argument. But yeah, again, I can compute it in the case I know best, this K and A and this sub variety. And there I compute the restriction of certain special divisors that arise from the geometry of this situation. But yeah, again, thanks to this fact that this automorphism deform everywhere, I can do my computations where I want. And this is of great help. So yeah, that's a bit the sketch of the theorem here. And now once I have this, then yes, then the last thing is that once I have that this I star induces an isometry kz multiplied by 2 with wkz, then from this I get that H2 transcendental of wk is Hodge isometric to the Hodge2 transcendental of the K3 surface by definition. And then this by result of Mongardi and also Eddington, that are independently. This implies already that WK is moduli on stable sheaves on SK for some Mukai vector. So that's how I get this. And yeah, this is a general result that any K3n projective whose transcendental lattice is that of a K3 is actually a moduli space on the K3. You have a question?
Yes. So do we know what is the explicit expression of this Mukai vector V?
No, we don't know. It's implicitly, and it's part of some. Yeah, I mean, I tried. So for in dimension 6, I have some more concrete ideas, and I think there I can do some calculations to see what this Mukai vector is. But yeah, there is no. It's just an abstract existence result. It would be very interesting, but. For the moment, I only have some guess through lattice theory, basically. But yeah, that's a good question.
And also, in your proof, the part that you need this Fujiki relation to do the computation is to prove the isomorphism over Z. So over Q should be, yeah, okay, but
Yeah.
what is over Z? That's it.
Yes, exactly. Because then I need to understand. So, I mean, I skipped some part, but after that, I really need to show this is a saturated embedding of lattices. So I need to analyze it more carefully than what I said here. But you are absolutely right.
Do you also use the result by Kamenova, Mongardi about the fixed point locus of?
Yes. This is used here because you see, I gave this description of this component, but this is only the description in the symmetric power of A. And you can see that this is basically in the symmetric power of A, you have something like A1 sim M in A0 M plus 1. And now this result by Mongardi Kamenova tells you that when you take here the resolution coming from the Hilbert-Chow resolution, here you get really the Hilbert scheme, the natural crepant resolution of this guy.
Mhm.
So the fact that you get this here, I use the result of Kamenova, Mongardio, Blanco, because there is some analysis to do on the fibers of the Hilbert-Chow morphism. And in low dimension, this can be done by hand. It's quite easy, but in general, they use quiver varieties. So it's more delicate, and I use their results.
Mhm. I see.
Yeah.
Thank you.
Yeah, so this is a bit the proof of the result. And now, okay, I used almost my time, but I just want to say what's the some consequences. So what's the relation with this Weil fourfold I started with? So these Weil fourfolds appear naturally in connection with the Cum-N varieties. This was done by Markman and O'Grady. A Cum-N variety K has B3 non-zero. So the third Betti number is equal to 8. And moreover, the odd structure is, there is no H30 part. It's only H21K plus H12K. So this gives me J3K, the intermediate Jacobian. This is actually an abelian variety whenever K is projective. And now what Markman and O'Grady realized is that J3K is a fourfold of Weil type and discriminant 1. So the results that Markman gets for these Hodge Weil classes for these Weil type fourfolds with discriminant 1 comes really from this relation. So he's able to construct some cycles on Cum-N varieties and then use them to get some cycles on their intermediate Jacobians. And for an hyperkähler X, there is another way to associate to it an abelian variety, which is by going, I mean, this is specific to Cum-N type, but in general, you can take the Kuga-Satake abelian variety, which is just built from the Hodge theoretic data, which is given on the second cohomology. And now part of the results here is that the Kuga-Satake variety of a Cum-N variety is isogenous to a power of J3K. And moreover, so the key property of the Kuga-Satake variety is that there exists an embedding of Hodge structures of H2 into the endomorphism of the Kuga-Satake variety. And then one wants this to be algebraic according to the Hodge conjecture. So the Kuga-Satake correspondence is algebraic for any Cum-N variety K. And this Kuga-Satake correspondence is, as I said, an embedding from H2KZ into the endomorphism of the Kuga-Satake varieties. One then actually can view it as a mapping to the H2 of the Kuga-Satake, but squared. Maybe it's better to work with Q coefficients. So this is the Kuga-Satake correspondence, and one wants it to be algebraic. This is a very difficult problem in general, but already for K3 surfaces. But for these varieties, it was completely proven by Markman and Voisin. And so corollary I want to mention to finish is that if K is Cum-N type, and I take Sk, the associated K3 surface, Then the SK come in countably many families four-dimensional families of Picard rank 16, and the Kuga-Satake correspondence is algebraic for each SK. And moreover, this is thanks to a result of Varesco. So it's a consequence of the previous statement by result of Varesco. The Hodge conjecture holds for any power of SK for any projective Kuman variety K. So in general, for K3 surfaces, the Hodge conjecture is of course known because they are surfaces, but the Hodge conjecture for their powers, it's open. It's only known for K3 of large Picard rank, basically, as well as the Kuga-Satake Hodge conjecture. Mostly they were known for Kummer surfaces. But a Kummer surface has a Picard rank at least 17. So here we find the families which have actually they contain the family of Kummer surfaces, but they have dimension one more. And we can prove now that there are this many, countably many new families of K3 satisfying both the algebraicity of the Kuga-Satake correspondence and the Hodge conjecture for all powers. Before, I think there were a few families of general Picard rank 16, of general Picard rank 16 that were known to have this property, namely one of Paranjape double covers of P2 branched in 6 lines. And not much more. So this is a corollary that we get. And now, I think I used maybe more than 90 minutes, but so I'll stop here. Thanks. Thank you very much for the attention.
Yeah, thank you very much. So are there any questions from the audience?
So O'Grady Markman result is for any generalized type, generalized Kummer type.
Yes.
Variety.
Yes. So the proof is actually very interesting. Basically, you look at so the H3 is essentially the Kuga-Satake, right? Is the H3 is the Hodge structure H1 of I mean, it's not the Kuga-Satake, but there exists this abelian variety A, this intermediate Jacobian, and then the Kuga-Satake is A to the 4th power. That's what they show. So you basically want to find a cycle from H2 onto the H3, in a sense, into H3 tensor H3. And what they do is to prove that the dual cycle is algebraic, basically. And how does it go? So you go from H3 tensor H3. Now this bicup product given by a cycle goes to H6. But then there is the so-called class Q in H4K. This is the Boville-Bogomolov cycle. So H4K contained seems 2 of H2. And you get the class of the form, give you a Hodge class here, which remains Hodge everywhere. So now you take intersection with a suitable power of Q, so that you arrive into the 4n minus 2 cohomology group of K. Because now this is, as Hodge structure, this is isomorphic to H2 up to Tate twist. And so you get a map here, this composition. And now you use the so-called LLV Lie algebra to conclude that this is a morphism of representations for basically you have an action of the orthogonal group of K on whole the cohomology. Here it's actually a spin action, but this map is equivariant, and this is absolutely reducible representation. So this map is either surjective or zero, and they show it is surjective. But now why it's given by an algebraic cycle? The point is that the class Q is algebraic. This is what Markman proves, that this class Q is algebraic. And therefore here, this is cap product, so it's algebraic. So here we have defined an algebraic morphism. But yeah, the point is that one needs to know this Q is algebraic, and this Markman proves by deforming certain hyperholomorphic bundles.
And if we want to just prove the Hodge conjecture for a power of a abelian surface, so do we need yeah, we don't need hyperkähler, or we still need, we don't need.
No, for power of abelian surfaces, the argument, classical argument of Mumford and Tate works, because it's just you show that everything is intersection of divisors. The thing is that when you have a generalized Kuhn, so the conjecture was known. Yeah, so for instance, for K and A, the Hodge conjecture is known. Because this is motivated by the abelian surface. And in this case, the Weil type fourfold, so the H3 of this, becomes the H1 of A times A dual. And then when you deform, this A times A dual will deform to a simple fourfold of Weil type. And there, the Hodge conjecture was it's more difficult. But for powers of abelian varieties, also of dimension 3, at most dimension 3, you take a power, then every Hodge class is just intersection of divisors. So this was known. The hard case in dimension 4 is really this Weil fourfolds. Even though, yeah, now Markman has a proof that doesn't rely on hyperkähler. He actually has a technique to deform sheaves directly on abelian varieties. And with this improvement, he's been able
to prove the Hodge conjecture by deformation for these varieties.
Yeah, exactly. He can now prove it for all of them, because the issue here is that as Kugasatake of varieties, you only get these fourfolds with discriminant 1. And this is an invariant. So this invariant actually takes place if you have a fourfold with action of Q square root of minus D. So let's call it K. Then this discriminant is some discrete invariance which takes value in Q modulo the norms of this field K. And when this invariant is trivial, then you actually get these fourfolds in this way as H3 of some Kuhn varieties. But when this invariant is not trivial, I think they are not even Kugasatake varieties. So it's, yeah. So, I mean, the new proof of Markman is it's much stronger. Yeah. I mean, I think it's quite spectacular result that he can complete the proof for all fourfolds of abelian fourfolds. Yeah, but I mean, I want to study the paper, but it's 90 pages.
Very long paper. Yeah.
Yes. Yeah. I mean, at some point, I hope to study it soon. I think I heard actually that Giuseppe Ancona, you know, this Java school. Yeah, I think we met there actually once. And I think Markman will be the expert for next year. Not this year, but next year. So I plan to go there and try to understand something. Yeah.
Okay, thank you.
Thanks for the questions. So are there any more questions from the audience?
So if we go back to the original, like one of the motivation is like you want to construct some explicit examples of
Mhm.
Coombe N type varieties. So do you think your theorem would help?
But yeah, I mean, philosophically, yes. In in practice, I think it's a bit too weak for the moment. But because what I had in mind is that in a previous work, in the special case of dimension 6, so the Coombe 3 manifolds, I can show that if K is any Coombe 3, then there exists a certain group G isomorphic to Z mod 2 to the 5, which is contained in the automorphism of K trivial on H2. And it is such that I can take K divided by G, and then there exists a Crepant resolution, YK, which now is of K3 type. So every Coombe 3 variety is a rational 2 to the 5 to 1 dominant cover of some K33 type. And in fact, also with arguments similar to this, when K is projective, this Y becomes a moduli space on a K3V. So in this case, I really hope, I'm trying, but I really hope that I will be able to construct some Kummer sixfolds of Picard rank 1 by starting from a K3 surface, finding a suitable moduli space. Here we also have some condition which ensure that this comes from such a construction, and then find a cover. So what I presented today is like a first step to go from Coombe 3 to Coombe N, because this construction doesn't work like this in other dimensions. So for any other group trivial on H2 on a Coombe N with N not 3, the quotient will never have a hyperkähler resolution. So I've been thinking if there were some different ways to get K3 associated to it, but of course the result I presented for Coombe N are somehow weaker than this construction. So I would hope in this case to get some model, and somehow it's similar. This K3 is very related to the K3s I presented today. And on the other hand, I think this SK associated to K of Coombe N type. So there is this work upcoming of Bayer, Perry, Pertusi, Zhao, and they construct Coombe N as they essentially construct Coombe N varieties as equivariant moduli of sheaves on some K3s. And I think the K3s that they find must be, if not the SK, something very related. So I don't know. I hope perhaps what I did and combine maybe can help together with what they do to give some explicit construction. Because yes, I think the result will be very general, and then they somehow will be able to construct abstractly every Coombe N. At least that's what they said in a talk I saw. Every Coombe N variety has an equivariant moduli space of sheaves on a K3 surface. But somehow I'm aiming for some more geometric description.
Nice.
So yeah, in this case, I'm more hopeful, and I'm attempting to find something similar in other dimension, but it's much harder. So this is a first step.
Yeah, thank you.
Thanks for the question.
Okay, any other questions from the audience? Comments? Okay, then yeah, thank you very much for the talk. Let's thank the speaker again.
Thanks. Thank you very much for the invitation and the attention.
Yeah, thank you very much. It was a nice talk.
Thanks. I try to motivate a bit the things. It's not easy not seeing the audience. What?
Yeah, sorry about that, yeah.
So
I
today
don't
there's
know.
no camera on.
Yeah, usually there's a camera, but
So we're in a different room.
yeah, in this room, no camera.
I see. Yeah, no worries.
By the way, maybe another quick question. I didn't want to keep people here, but so is there any similar kind of relation between upgraded 6 and upgraded 10s? Like, can you know?
Yeah, that's also a good question because so for O'Grady 10 and so Betty number is 24. So for a very general, there is no way that the odd structure is that of a K3 surface. But a very interesting case is that of OG6. The second Betty number is 8 now. And in fact, somehow the lattice is very similar to, so the lattice here, the H2, is 3 hyperbolic plane plus -2 plus -2. While if I take the H2 of cum n, this is 3 hyperbolic planes plus a class minus 2n plus 1. So essentially, here I can look, if I look at OG6, where this class stay algebraic, say. Now I can identify basically the period domain of OG6 with this class algebraic, with essentially the period domain of cum n of the right. For instance, cum 3 will work. And therefore, if I take OG6 with this -2 class algebraic, then by Hodge theory, I can again associate to it a K3 surface Sk, and this will be the same as some K3 surface Sk for K some variety of cum n type. But what's very interesting is that here, for the very general OG6, actually this class will not be algebraic. So actually any OG6 by Hodge theory, I can associate to a K3 surface, but now they will form a family of dimension 1. So if I look at projective OG6, I have a family of dimension 6.
So if we look at the original example of O'Grady, then what is the class of the expressional divisor from the symplectic resolution?
Yes. So it's exactly this -2, because basically you can look, for O'Grady case, you look at A, but then you take a moduli, which is with Mukai vector 2, 0, -2. And now, okay, you take the moduli 2, 0, -2. Now this has an Albanese fibration to A times A dual, and this I denote the fiber. Now it is known that the H2 of the singular, so this is a singular OG6 variety, because O'Grady shows there is a desingularization of OG6 type. Now there is a theorem similar to the theorem for K3 surfaces, that the H2 of this, it's actually isomorphic to 1, 0, -1 orthogonal in the Mukai lattice. And then when you, and so this, you can compute that this is exactly H2A plus -2. And then when you resolve it, the class of the exceptional divisor is a class which is again, then when you resolve it, if you look at H2K tilde, this will be H2KA, so the singular model. Then you have plus, basically the class of the exceptional divisor is divisible by 2. So that's so this class will have square -2, but it is, yeah, twice it is the class of the exceptional divisor. And so basically I'm just, what I said is that if I just look at these, the locally trivial deformation of this, so I keep the singularity, then they have a resolution. Those OG6 by OG theory are associated to some of the K3 surfaces Sk that I associate to cum and varieties. But in case I have OG6 which does not come as a resolution of such a thing, so I allow this divisor here to become non-algebraic anymore, I get a family of one dimension more of these hyperkählers. And in fact, I think it would be very interesting because in a paper we are working on with Lie Fu, if I have that my K tilde OG6 is a resolution of such a singular thing, then the Kuga-Satake is again isogenous to a power of Weil fourfold with discriminant 1. But if I take K very general projective OG6, now H2 transcendental K has rank 7. So the Kuga-Satake of this K is not of this form. It's a bigger family of abelian varieties. And I don't know if this is described. I mean, I would be interested in finding a description of Kuga-Satake varieties, because the trick for the results I discussed, also the ones of O'Grady and Markman, is that a theorem of Lombardo describes the Kuga-Satake of a Hodge structure on a rank 6 space, which looks like this. So if I have a K3 type Hodge structure on a quadratic space isometric to this, where A and B are any integers, then Lombardo tells you that the Kuga-Satake is a power of Weil fourfold. But Weil fourfold with discriminant 1. But in this case, for a very general OG6, I will have some lattice, which is U. Yeah, I don't even know. There are maybe various possibilities, but it should be some U2 plus basically minus A, minus B, and minus C. And I don't know if somebody has described the Kuga-Satake of an irreducible Hodge structure on such a quadratic space. I think it will not be of Weil type, because somehow, you know, for the Kuga-Satake, you build them through the Clifford algebra. And basically, this action of this quadratic field comes from the center of the Clifford algebra. But if you start with the odd dimensional space, the center of the Clifford algebra is trivial. So I don't expect them to be of Weil type for sure. But yeah, would be interesting.
Yeah, thank you very much for answering also the extra questions. Yeah, thanks for the nice talk in general. That's very nice.
Thank you very much for the invitation.
Yeah,
Thank you.
then we're gonna get closing the call. So yeah, bye-bye.
Bye.